For over a century, the idea of faster-than-light travel has captured the human imagination. From Star Trek to science classrooms, the dream of zooming between the stars in a matter of minutes has inspired scientists, engineers, and storytellers alike. But what if this dream isn't just fiction? In this video, we'll explore the real-world science behind warp drives, the bold research being led by NASA, and how new discoveries are bringing us closer than ever to rewriting the limits of space travel. From warp bubbles to exotic matter and even extra dimensions, this journey will take us deep into the frontier of theoretical physics. So buckle up, and let's dive into the science of the impossible. The modern idea of a warp drive began in 1994, when Mexican theoretical physicist Miguel Alcubierre proposed a solution to Einstein's field equations that allowed for faster-than-light travel, without violating the theory of relativity. The key idea, a warp bubble. Instead of moving the spacecraft itself faster than light, Alcubierre's model proposed that we move space itself. You'd contract space-time in front of the ship and expand it behind. The craft wouldn't technically move at all. It would ride a wave of warped space, like a surfer riding a wave across the ocean. This model was revolutionary. For the first time, faster-than-light travel was shown to be mathematically possible. But there was a catch, an enormous one. Initial calculations showed that creating such a warp bubble would require a massive amount of energy, more than the mass of Jupiter, converted into negative energy. And this wasn't just about quantity. The type of energy required was a much bigger problem. It involved something entirely theoretical: exotic matter with negative energy density, a concept predicted by quantum field theory but never observed in nature. This is where Dr. Harold "Sonny" White enters the story. Dr. White, a physicist at NASA's Johnson Space Center, revisited Alcubierre's equations and proposed a crucial improvement. Instead of a spherical warp bubble, he designed a toroidal shape, more like a donut. Why does the shape matter? It turns out the geometry of the bubble affects how space-time is distorted, and in this case, the toroidal version drastically lowered the energy requirements, from a Jupiter-sized mass down to the equivalent of 700 kilograms of mass energy. Still extremely high, but a leap toward feasibility. This reimagining of the warp bubble rekindled serious scientific interest in the concept. To test warp field concepts experimentally, White's team built a device called the Juday Warp Field Interferometer. It's designed to detect tiny distortions in space-time, potentially generated in the lab under controlled conditions. Think of it as trying to detect the ripple of a pebble in a cosmic ocean. The signals would be incredibly subtle, but if detected, it would be the first experimental sign of a warp field. Though no warp bubbles have yet been conclusively observed, this work marks the first tangible steps toward validating a theoretical model once dismissed as pure fiction. You might be wondering, what is this so-called exotic matter, and why is it so important? In simple terms, exotic matter is hypothesized to possess negative mass and negative energy density. Unlike ordinary matter, it would behave in bizarre ways, accelerating toward a push rather than away from it. It's this strange behavior that could, in theory, stabilize a warp bubble and allow space itself to bend and move. While exotic matter has never been observed directly, certain quantum effects, like the Casimir effect, have produced tiny regions of negative energy under very specific lab conditions. But turning this microscopic effect into a scalable propulsion method, that's still a massive leap. The Casimir effect occurs when two metal plates are placed extremely close together in a vacuum. Quantum fluctuations in empty space create a pressure that pushes the plates together, a phenomenon that can only be explained by negative energy density. Some researchers believe this effect might point toward a way to engineer exotic matter or manipulate spacetime on small scales. However, recreating it on a macroscopic level, large enough to move a ship, remains one of the biggest hurdles. Still, it's one of the few experimentally verified hints that exotic energy could exist. According to Alcubierre's and White's theories, a spacecraft inside a warp bubble wouldn't actually be moving in the conventional sense. Instead, it would be stationary relative to its local spacetime while the space around it is compressed and expanded. This means the ship wouldn't experience time dilation or extreme g-forces, since it's not accelerating through space. It's the space that's moving. In theory, this method allows for faster-than-light travel without breaking the cosmic speed limit. This concept is revolutionary not just for propulsion, but for how we understand motion itself. Warp drives aren't the only game in town. Other theoretical frameworks are being explored as potential methods for interstellar travel. One idea involves wormholes, hypothetical bridges that connect distant points in spacetime. These could theoretically allow for instantaneous travel across the galaxy, but would also require exotic matter and stable structures that we don't yet know how to create. Another promising area of research lies in extra dimensions. According to string theory and brain cosmology, our universe may contain hidden spatial dimensions beyond the familiar three. If we could access them, we might discover shortcuts through higher dimensional space. However, just like warp bubbles, these ideas remain speculative. No empirical evidence currently supports the existence of wormholes or extra dimensions, but they continue to inspire new directions in physics. Finally, some scientists are investigating dark energy, the mysterious force causing the universe to expand at an accelerating rate. If we could understand and harness this force, it might be possible to create localized expansions and contractions of spacetime, similar to a warp field. It's a long shot, but dark energy is one of the biggest mysteries in physics. Solving it could change everything, not just space travel, but our fundamental understanding of the universe itself. Warp drive technology is still far from reality. The challenges, technical, energetic, and theoretical, are enormous, but the progress being made, especially by researchers like Dr. White, is steadily moving warp drive from the realm of science fiction into the edges of possibility. Even if we don't achieve faster-than-light travel in our lifetimes, the pursuit itself is valuable. It drives innovation, fuels new discoveries in physics and engineering, and challenges us to think beyond the limits of what we believe is possible. So, could warp drives become real? Not tomorrow, maybe not even this century, but the seed has been planted, and it's growing. What was once the domain of science fiction is now a subject of serious scientific inquiry. If humanity is to become an interstellar species, this is the path forward. Thanks for joining us on this journey through warp drive theory and the future of space travel. If you found this video fascinating, give it a like, subscribe, and hit the notification bell so you never miss our next deep dive into the frontiers of science and technology. Until next time, keep imagining, keep questioning, and always keep looking up.